An application's resilience is completely dependent on the integrity of the health checks monitoring it. If domain name system routing mistakenly sends client traffic to a node with a degraded processor or a crashed local storage drive, the user experiences an immediate hard failure. Amazon Route 53 health checks operate as the automated monitor at the network edge, maintaining continuous, real-time telemetry on endpoint responsiveness. To build systems that repair themselves without human intervention, we have to analyze the exact mathematical thresholds, transport protocols, and architectural configurations that make zero-touch failovers possible. This requires designing telemetry models for both public-facing networks and completely isolated private virtual private clouds. Mastering these internal mechanics is the only way systems architects can guarantee a resilient, self-healing infrastructure. The baseline architecture of Route 53 relies on a global fleet of approximately 15 geographically distributed health checkers. These checkers evaluate endpoints using 3 standard transport layer protocols: HTTP, HTTPS, and TCP. When testing via HTTPS, the checker demands a full SSL/TLS handshake to validate the cryptographic layer before passing the endpoint. Under standard settings, checkers pull resources at a 30-second interval. For highly critical paths, you can accelerate this to a 10-second fast polling interval. This acceleration comes with a direct operational cost, as it triplicates the total query volume continuously hitting your target servers. To toggle an endpoint state, Route 53 requires either 3 consecutive successful probes or 3 consecutive failed probes. A probe registers as a failure if the endpoint returns an HTTP response code in the 4XX or 5XX range, or if it simply fails to respond within the standard network timeout window. Even if a single checker detects a failure, it cannot trigger a failover independently. The system requires global consensus. Route 53 dictates that strictly more than 18% of the active global checkers must report a healthy status to maintain active routing. Looking at this global map, we see the 18% threshold in action. With 15 active checkers, at least 3 nodes must lock in a healthy reading. If healthy reports drop to or below 18%, Route 53 instantly isolates the target and cuts off DNS routing. This strict consensus math ensures that transient, localized network glitches do not trigger false failovers. Beyond evaluating raw status codes, Route 53 can perform application layer validation by parsing the actual body of the HTTP response. You can configure the checker to look for a specific custom string, requiring the application to explicitly return a phrase like database connected. This diagram illustrates a critical mechanical limitation. Route 53 strictly evaluates only the first 5,120 bytes of the response. If your endpoint returns a massive document and the success string is pushed past this boundary, the health check automatically fails. The architectural solution is to design lightweight, dedicated custom JSON endpoints that return the status string instantly in the initial response block. To allow this external probing, your VPC security groups and routers must be explicitly configured to permit inbound traffic from Route 53's external health checkers. Engineers pull these specific external IP addresses directly from AWS's officially published public-IP addresses.json file. Text validation provides deep application insight, as long as engineers tightly control their endpoint response payloads to fit within these strict mathematical limits. Because Route 53 checkers reside out on the public internet, they inherently lack access to private subnets or private hosted zones. Standard probing will automatically fail against any private endpoint, hidden securely behind internal firewalls or NAT gateways. To monitor these isolated resources, we have to invert the architecture using CloudWatch alarm integration. First, the private backend nodes are configured to stream local performance telemetry, such as CPU utilization or available disk space, directly to Amazon CloudWatch. This schematic shows how Route 53 connects. Instead of polling an IP, it uses an internal API to monitor a specific CloudWatch alarm. If that internal metric triggers an alarm state, it automatically and instantly flags the Route 53 health check as unhealthy. This inverted architecture bridges the telemetry gap between public edge networks and isolated private subnets, maintaining strict internal network security. For multi-tier applications, checking a single endpoint lacks the visibility needed to assess complex, distributed systems. Route 53 offers calculated health checks to achieve multi-dimensional architectural visibility. Unlike standard checkers, calculated checks do not pull endpoints directly. Instead, they aggregate the active statuses of other existing health checks. They evaluate these statuses using standard Boolean logic operators, and, or, and not. This logical tree diagram shows a master check. By inserting an AND gate, the master node is healthy only if both the web tier and background queue operate normally. Administratively, a single calculated check is limited to aggregating a maximum of 256 underlying checks. Calculated checks empower architects to govern global DNS propagation based on complete, holistic system health, rather than relying on the isolated status of a single server. We connect all of these telemetry mechanics to execute automated disaster recovery using an active-passive failover routing policy. This setup involves provisioning a primary active resource alongside a redundant standby resource located in a completely separate availability zone or AWS region. Under normal operating conditions, Route 53 validates the primary resource's health check and consistently returns its designated IP address to clients. Detecting an unhealthy state on the primary forces Route 53 to automatically bypass the primary record and begin routing traffic to the standby resource. The exact failure detection timelines require strict calculation, as this math defines an organization's recovery time objective, or RTO. This timeline maps the detection window. 3 10-second failed probes equal a 30-second detection window, while standard 30-second intervals stretch this to 90 seconds. Additionally, downstream caching by ISPs or browsers ignores the updated DNS record for the duration of its time to live. To mitigate these caching delays and minimize the true RTO, best practice requires combining low record TTLs with dynamic alias health checking. By mastering polling intervals, payload limits, and consensus math, systems engineers can guarantee their DNS layer instantly and dynamically aligns with their physical compute infrastructure.